You know, the ground we live on, the ground we walk on every day, it feels completely solid. But deep inside our planet, there are these huge, powerful forces constantly at work. And these are forces that can literally shake cities to the ground and send massive waves racing across entire oceans. So today, we're going to explore that raw power, the power of earthquakes and tsunamis.
And that's the thing, isn't it? That's the fundamental and, yeah, kind of terrifying truth we're starting with. That feeling of stability, it's really just an illusion.
Way down deep beneath our feet, and under the vast oceans, the Earth's crust is actually this mosaic of massive plates that are in constant grinding motion. So in this explainer, we're going to uncover how all that friction deep underground unleashes the energy for earthquakes, and then how those quakes can create some of the most destructive waves on the entire planet.
Okay, so let's get a clear definition on the table. What is an earthquake? Well, at its heart, it's just the planet shuddering. It's a sudden, violent release of all this pent-up energy that sends vibrations. We call them seismic waves, racing right through the Earth.
So first up, let's talk about the immediate effects of these events. What does an earthquake actually look and feel like, both for people on the ground and for the scientists who study them? To really get what's happening way down deep inside the Earth, we have to put on our detective hats. And our main clues? They're the seismic signals, those energy waves that every single earthquake sends racing through the planet.
So this is what an earthquake looks like to a scientist. An instrument, it's called a seismograph. It records these energy waves as they travel through the planet. And what you'll notice is that they don't all show up to the party at the same time. First you get the P waves, then the S waves, and finally, those really destructive surface waves.
And this is where it gets really interesting. The difference between these two body waves that travel right through the Earth's interior. You've got P waves, or primary waves, and they're fast. They compress and expand stuff kind of like a sound wave, and they can go through solids, liquids, and gases. But then you have S waves, or secondary waves. They're slower. They move side to side more like a light wave, and here's the kicker. They can only travel through solids. That's a super important clue.
So what happens when these waves hit the Earth's core? This is the big reveal. Seismographs on the complete other side of the planet will detect P waves, but they don't detect any S waves. This creates what's called a massive shadow zone. And this just brilliantly shows us how we know the Earth's outer core is liquid, because those S waves simply can't get through it. It's like getting an X-ray of our own planet. Absolutely brilliant. Okay, so we can read the signals an earthquake sends out. But what's the engine behind all this? What's actually causing the quake in the first place? Let's go find the culprit.
Right. Welcome to the engine room of our planet. See, the Earth's crust isn't one solid piece. No, it's broken up into these enormous slabs called tectonic plates. And these plates, they're always moving. They're colliding, they're pulling apart, and they're sliding right past each other at their boundaries. And when you look at the data, it's crystal clear. An overwhelming 80% of all earthquakes happen right where these plates meet. All that friction and stress building up at the margins, that's the main source of the energy that eventually gets released as a quake. Now there are two key terms here that are super helpful to know. The focus is the actual starting point of the quake, way down deep in the crust. But the word we hear all the time is epicenter, and that's the spot on the surface directly above the focus. It's usually where the most intense shaking is felt.
All right, now we get to connect the dots. How does the ground shaking create these monster waves in the ocean?
So how does a little tremor on the seafloor become a giant, towering wave? Well, it all starts with a sudden, violent shift. One tectonic plate shoves the seabed straight up, and in doing so, it displaces this massive column of water. Gravity pulls that mound of water back down, and all that energy just explodes outwards as a wave. You know, out in the deep ocean, you'd barely even notice it, but as it races toward land and the water gets shallower, the wave slows down, it compresses, and its height just explodes, creating that terrifying tsunami wall. And just to give you a sense of the insane power we're talking about, out in the deep ocean, a tsunami can travel at 800 kilometers an hour. I mean, that is literally the cruising speed of a commercial jetliner. It's just pure energy, moving silently and almost invisibly across the ocean.
Yeah, and we are not talking about your average beach wave here. Not even close. Just look at the comparison. A normal wind wave might have a period of, say, 20 seconds, a wavelength of 200 meters. A tsunami's period can be up to 2 hours, with a wavelength stretching over 500 kilometers. It's not really a wave in the way we think of it. It's more like the entire ocean level suddenly and violently rising.
Okay, so now that we get the how, let's zoom out and look at the where. Where on Earth do these destructive events happen most often?
And this is pretty much the most seismically active place on the entire planet, the Circum-Pacific Belt, much better known as the Ring of Fire. It's this massive arc of fault lines and volcanoes that stretches all the way around the Pacific Ocean, where the huge Pacific Plate is just grinding against a bunch of other continental plates. And the numbers really back this up. A whopping 65% of the world's earthquakes happen right along this Ring of Fire. The Mid-Continental Belt, that's where you find the Himalayas, that gets about 23%, but the Pacific is without a doubt the hotspot.
And the consequences? Well, they can be absolutely catastrophic. The 2004 Indian Ocean event is just a tragic reminder. A massive magnitude 9.0 quake hit right on the Ring of Fire. It unleashed a tsunami that became one of the deadliest natural disasters in recorded history. It took over 230,000 lives across a dozen countries.
You know, when you think about events like the 2004 tsunami, you see the devastating human cost. And that brings us to a really crucial question. How can we use all this scientific knowledge to measure these events and hopefully save lives?
Okay, so when a quake hits, you'll hear people talk about two different scales. The light bulb analogy is the best way to think about it. The Richter scale, that measures magnitude. That's the wattage, right? The raw energy the bulb puts out. But the Mercalli scale measures intensity. That's how bright the light feels from where you're standing. So a quake has one magnitude, but it can have a lot of different intensities depending on where you are.
And this is where the science is just incredible, where it really makes a difference. Look, we can't stop the earthquake, but we can detect the tsunami it creates. Systems like these DART gauges, they use sensors way out in the deep ocean to detect these tiny little pressure changes from a tsunami wave passing overhead. That data gets beamed up to a satellite, allowing for warnings to be issued, sometimes giving people up to 3 hours before the wave hits the coast. That saves lives. And that leaves us with this one big final thought. Our understanding of how the planet works has allowed us to build these amazing systems that can save lives by forecasting the effect, the tsunami. But predicting the cause, the exact time and place of that initial earthquake, well, that remains the holy grail of seismology, and it's a challenge that, for now at least, seems to be just beyond our grasp.